So thank you very much for the invitation, and I'll make a few preliminary remarks before I actually put up the title of the talk. But I think it's probably fair to say that our community is very data-based, and we've done lots of empirical studies. And one of the problems is sometimes you go to education conferences and this scenario plays itself out, and you sort of put your data up and someone says, what's your theoretical framework? And I have to say, I always go cold and I think of all those things, you know, like I feel I must say constructivism, Piaget, Vygotsky, socialism, discourse theory, and LCT, and do you know what that is? Okay, that's one that Cedric probably knows that one. It's the legitimation code theory, which somebody just used for their thesis. But all of these things make you think, you know, yikes, you know, and all of these things are sort of grand theories. So it always works when you test it. So I think, you know, theory is a very broad landscape. And I mean, it comes along with classification schemes. One can impose theory, you know, one can use theory, and I think one can generate theory. So I think a lot of the talk here is about an approach to theorizing physics education research through the traditions that we have in physics. And so I'm going to do a little bit of nuclear physics and show how, you know, theorizing there works. And I'm going to propose that PER is like that. Now, that could be entirely wrong, and so it's in the spirit of being criticized later that I actually hope everybody will listen to this talk. So it's generating theory from empirical data, and okay, and so the title of the talk of humble theories. So I need to acknowledge a couple of people, and the first thing is one has to acknowledge the organizers. And this is a very nice picture of Cedric, a very nice picture of Rebecca, and then a picture. He says that's fine. But the sort of work that one does, I think, if one has any success, you know, it depends on huge numbers of colleagues. I mean, and it's impossible to list them all. But I do want to mention, and I'll be drawing on the work of a lot of the colleagues. There's the work that I did in measurement with Andy Buffler, Fred Lovenbach, Campbell from the University of York. Then a lot of the studies which underpin what I'm going to say came about from master's and PhD work, and that's Trevor and a whole crowd of people. And then I do need to acknowledge Joe, and I have a special picture which I think Joe would like, so I'll put that up at some point. And then I particularly want to thank Deidre, you know, Demory, who's about to settle for South Korea, I believe. And, you know, some of the work that we did was actually very exciting. So the other sources I want to acknowledge are that I've looked into the design-based research literature, which I find very interesting. I don't want to get carried away with that, but I think it's an interesting model for us to look at. And the papers I've drawn on are not very well referenced there, but it's Prediger et al., in a very strange journal of mathematics, which, as my colleague said, contains mostly science, and then a paper by Besessa and Cobb on something called ontological innovation. And then finally I want to just thank these people who are over here, and that's a discussion group that I've had over the last couple of months, maths educator, engineering educator, and my colleague Dan Taylor was in physics education, who attended AAPT last year. So I'm going to start here with a diagram which I think many of us know, and it's the enterprise of physics, and it's an adapted version of the well-known diagram by David Hestenes in the American Journal of Physics, modeling games in the Newtonian world in AJP 1990. So in this model, he looks at physics, and I think for me it was a very illuminating moment to think of physics in this way, and physics consisting of the physical world and then a conceptual world. And in some ways one can look at this as experimental physics and theoretical physics, and they are linked together by these things over here, by representation and by interpretation. And that's the two things that keep the theory grounded in the real world and illuminated, and the real world illuminated by the construct of the theory. So that's the first part, I think, and I think that it's also interesting to realize that, all of that's mediated by the way we think about these, all of that's mediated by the way we think about both the real world through observation and actions that we actually do, experiments that we do in the world, and then constructing conceptual models which other people have to understand, and that's the sort of education side of things. And then this year is something I'm going to talk about in a moment. So that's the sort of basis of what physics is about, and I think if one sees those three elements, it actually makes it a lot easier to actually see physics as an enterprise. It's very interesting. I always use this in a physics education research module that I teach, and you get a lot of sort of hard-nosed students who sort of they have to do a few of these lectures. And after showing one of the students this, the next day I asked, how did you enjoy the lecture? And he looked at me and he said, it was surprisingly interesting. And I thought that was. So I'd like to read this here, and this is from a paper by DeSessa and Cobb, called. It's from the Journal of the Learning Sciences, and I'm going to read this, and I think it offers us something in the way of being able to theorize in the way I'm going to explain in a moment. So he says that, they say theories in science are a principal part of the power and elegance of science. They bring order to a vast array of seemingly disparate phenomena, teaching us how to see. The second point is, no psychological or sociocultural theory has the breadth, precision, and detailed validation of those in the physical sciences. And I think that's sort of obvious to all of us. But here's the interesting point he makes. He says, however, we see no reason to believe that the human sciences are essentially different. All sciences went through early stages where progress was chaotic and uncertain. And then he comes up with this very nice term, or they come up with this very nice term, ontological innovation, creating categories and theoretical constructs that empower us to see order and patterns in complex settings in which we conduct our, and in this paper it was about design experiments, and I'm suggesting we can put the word PER there. So here's the picture that so I'm going to put that on that previous diagram, but before that I just want to put this picture up here, and this is the metaphor of the brain as a city, and this is the picture that I think Joe would have liked. Okay, so I'm sorry he's not here, but I will actually give him a copy of this. This comes from a recent book, a PBS series as it is, by David Eagleman on the brain. So and it's a metaphor of the brain as a city. If you look closely, I'm not quite sure if you can see it, but those are all skyscrapers and roads, and it's the top view of a city. And it's really interesting. Sort of one of the things that he says in the book is, you cannot ask the question, where is the economy of the city? Okay, it's not a question that you can ask. And that's sort of the way one needs to think about the brain. So now, I'm going to put all of that together into the enterprise of physics, PER. Okay? And it goes something like this. If we look over here, we see a very complex world, right? And in our case, it's highly context dependent. I think that point was made earlier with the first speaker who spoke about the assessment instruments. Context is very important. But what we try to do out of those, we observe, right? And that's what we perceive various patterns, and then we want to theorize about that. And so I think this is very nice over here. We carry out an exercise of ontological innovation. So if you think of physics, what are those? What do we do? We create something called a point mass. Where do you find that? Only in physics textbooks and in the community. So we create something that really doesn't exist, well, doesn't exist if it's in your head, but doesn't exist out there. And we build a whole of Newtonian mechanics using ontological creations that allow us to simplify the problems and get insight into the complex world. So in a sense, what we've done is to go from this complexity, this complex engagement of the real world, to this here sort of portable knowledge that you can carry around with you. It's lifted out of the context. If we look at physics, I'm going to make the following assertion and then show you through the example of nuclear physics the following. That if this is theoretical physics over here, there are two kinds of theories that we find in physics. The grand theories, Maxwell's equations, but then we find humble theories. And I'm going to take you through a short bit of nuclear physics and convince you that nuclear physics is all about humble theories. So this is the enterprise of physics, nuclear physics. Now, in the late 40s and 50s, there was some pretty puzzling nuclear data. Well, firstly, whatever it is, it looked messy. Okay, it looks very messy. Okay, we can make sense of whatever it is. But what was interesting was that these are actually diagrams of binding energies, and they follow a nice pattern, except there are discontinuities when you have either the proton number or the neutron number. These numbers over here, they were called the magic numbers. Why they were there, why did these discontinuities arise, that was not known. So that's what things were like in the late 40s and 50s. And then the nuclear shell model was developed, and Maria Cooper-Mayer and Hans Jensen got the Nobel Prize in 1963. And I'd like you to read, and this comes from her Nobel Prize winning speech, and it's really interesting because I think it speaks to us as well. So the shell model corresponds to the experimentalist approach. That's us, okay. It was born from a thorough study of the experimental data, plotting them in different ways and looking for interconnections. This was done on both sides of the Atlantic Ocean, and on both sides one found that the data show a remarkable pattern. The discontinuities in the pattern were sufficiently marked and they could hardly arise from accident. It seemed to be worthwhile to attempt to explain them in the same way as the noble gases. Indeed, one might try to copy the essential features of the atomic structure for nuclear structure. So they use the analogy of atomic structure to develop a theory of nuclear structure. Actually, I wish someone had told me that when I did nuclear physics, because if I'd known that, I might have understood things, and it took about 20 years for me to figure that out. But anyway, it's quite an amazing thing. Now, she won the Nobel Prize. Now we go to, now think about it, I'll compare these things in a moment. But in December of 1938, Arnold Strassman, when they bombarded uranium with neutrons, they found isotopes of barium among the decay. So the question was, how could a tiny neutron possibly cause the nucleus to split in two to produce much lighter elements? That's very puzzling. And then, of course, Lisa Meitner, who didn't win the Nobel Prize, and one might suspect it was something to do with anti-feminism or anti-Semitism, but it turns out from the readings that I did that the Nobel Prize committee consisted of chemists, and of Swedish chemists, and they had no idea of the import of the explanation of Meitner and Frisch, her nephew, which was the following. And this is what they wrote in 1936 in Nature to explain how the nucleus could split into two. An essentially classical picture of these new disintegration processes suggests itself. On account of their close packing and strong energy exchange, the particles in a heavy nucleus would be expected to move in a collective way which has some resemblance to the movement of a liquid drop. if the movement is made sufficiently violent by an energy, such a drop may divide itself into two small drops. Now that's quite amazing, but what's amazing now is nuclear humble theories. If you look at these two models, it's very hard to see anything in common. I mean, the one consists of a series of steps, and a drop, well, that doesn't have any steps. And here we have two things which both attempt to explain features of the nucleus. If you compare them, you'll discover in nuclear physics, the landscape of humble theories in nuclear physics is very vast. And it's a huge and messy business. This is taken from one of the books that looks at, how they're related, and they're related at some very complex manner. It's not even clear that one will ever have a theory of nuclear physics at a fundamental level. It's just too complicated. But it's very interesting, if you look at the differences between the two, I see this in terms of context. And what is the context? The context is to what extent a neutron or proton experiences the rest of the nucleus. So if it's a big blue, if it's a single particle and it sees the rest of the nucleus, and you get a lot of steps. But if everything's tightly bound and you get a collective motion, you get the liquid drop description works better. And so I think that for us, and I think it's maybe worth a discussion at some point, seems to me a very nice paradigm for the way in which physics education research can be theorized. I think these humble theories went a long way to explaining these amazing phenomena in nuclear physics, and there's no way that the two things are related, or can be seen to be the same, other than at a very high, impractical level. Okay, so after that foray into nuclear physics, we come to something which is a bit simpler, but not really. So now let's look at physics education research in terms of generating a humble theory regarding student ideas about measurement. So I think many of you might have been familiar with this work, but just to look over it again, one of the things that we tried to do, and this was in the 1998 with the University of York, was to try and understand how students engaged with the collecting of data, how they made sense of it, and how that sense-making related to the more canonical versions of what we were trying to teach. And for that purpose, we developed the instrument, the Physics Measurement Questionnaire, and it involved this, a questionnaire which the questions were about, involved data collection, data processing, data comparison, and it all involved a ball that rolled down the slope and then ended up over here on the ground, and there were many questions about that. So the form of those questions, something along these lines, and it was the questions were framed in the way of debate, and the debate did something that, in this particular case, the issue was it necessary to repeat the distance measurement, the distance measurement being the distance that the ball landed on the ground from the edge of the table. So, the first student sort of offers the opinion that they should do it a few more times. The other one offers the opinion saying, well, they've done it, don't have to do that again. And the other one thinks they should do it at least once more. And that's interesting. That sort of offers the opinions. And then, of course, once students have committed themselves to an opinion, the most important thing is to explain the choice. Now, for that question alone, this is the amazing thing always about doing physics education research. There is no way that you could come up with a variety of reasons that people think, okay? Just that question alone, okay, don't have to look at it. Those are the different, and I think that there's another page like that. But that, be that as it may, that's not what I want you to look at. What I'd like you to look at is this particular one that someone wrote. And this makes no sense. Repeating will give different results, which is confusing. I want you to remember that, okay? And I mean, really, when I saw that, I was like, you shake your head, you think, wow, I'm confused, okay? How anybody can be that confused? But, okay, so then, you do all these data, you collect the data, and then you try to make sense of it. And the first time you tried to make sense of it was in terms of a sort of level student progression. So we had all these questions, put the students into different categories, and they fell into sort of a lower level, a more advanced level, and so on. So there's some level order, but very difficult to gain further insight into student thinking. There's no predictive power, there's no guide for future research. There's no simple guide for instruction either. So it's fine to add another level. That's what we did. I remember it was level H. It was like 10 levels, and I think we added an 11th or something like that. And then something like this happened, okay? Analogy, right? Thinking of these levels as excited states, also being fascinated by wave particle duality. They somehow came together, and suddenly, it was like, oh, this is interesting. Maybe there were only two things here. The one was, and as they ended up being called a point paradigm and a set paradigm. And so the point paradigm was when you thought about data as a standalone solid object. And the question is, how do you combine that? But if you think of the data, each data point as some kind of information, right, and you can combine these, and then the overall set properties can be used for further processing. So that immediately, gives you a tremendously powerful insight, if it's true, into how all these different results may be unified. So I always remember when we published this work for the first time, the referee wrote, he said, it is impossible that such a simple thing can explain all the data. But he wasn't able to show any of the data not being explained. So you gain from theorizing. This high level of complexity was simplified, and now you can see this thing that we all found amusing makes sense. Because if you think of data as, two hard objects, and you ask to combine them, well, that is confusing. How do you do that? It's like, it's asking one to do something that doesn't seem possible. The other thing was it offered a frame, a set of tools and predictions for the future, for future work. And so one of the predictions that we made was that if this is true, and we present students with a set of points that can be fitted by a straight line, if you fell into the point paradigm camp, you join the dots, and if you fell into the set paradigm, you draw a straight line. And in fact, that turned out to be the case, which is the thesis of Trevor Faulkner, which was in the previously called PERC. So suddenly, you have knowledge claims that are more portable, and they are less tied to the context in which you gathered them, and to borrow from that previous. On both sides of the Atlantic, it was found to be similar, and even on the same side of the Atlantic in Sweden, the studies that were carried out by Rebecca, who was from Maryland, they also turned out to be the same, and that's it's very nice. It was a very nice sort of powerful way of looking at things, and many other people have actually found something similar. But here's the other nice thing about it. There was a link to other theories, and in particular, it was linked to conceptual metaphor theory and to embodied cognition. And I don't want to go into that in detail, but for me, this is always a very nice So if you think of embodied cognition and conceptual metaphors, you can think of, if you consider the data, if you consider a set of wooden beads, okay, and they're all different colors, and someone says to you, I'd like you to apply some formula in order to produce an average bead which presents you with an average color. There's nothing else you can do but to try and select one of those beads. There's no way you can combine them. On the other hand, if you have a lot of soft clay beads, you can put them all together. And I presented this some time ago. I remember Joe was in the audience, and he immediately said, you can put them all together and make them into a big ball. And then you can create a new ball which will have the average color of everything. So those conceptual metaphors, and pursue that a little bit further into embodied cognition areas and so. But very nice when you have that insight, and suddenly you can see, this is why people think that way, and then what appears to be completely nonsensical suddenly make some sense. Okay. Now, the second example I'm going to give of this sort of humble theory is a much more speculative one, and but it shows some promise. And one of the big questions in PER is how do you deal with affect? That's not a simple business. Okay, so productive task engagement is affected by many factors which are sort of backstage cognition related. So the kind of way in which one thinks about data, for example, the metaphors that I showed, one can think of those as a sort of foothold metaphors. So the point and set paradigms would be the foothold metaphors that come to mind, one or the other, when confronted with a task and you have to engage with it. But at the same time, a large number of studies which, to do with the voice of the task, the audience dependence, the monitoring of threats and fear, which relate to stereotype threats and so on, all of these things show very clear effects when one presents students with any of these variations. So I think, Julian Taylor did work on audience dependence recently. My student Perry looked at something like that. But how do you take all this into account? It's not simple. And so that was the idea space model that was born, and Deidre and I pursued that. If David Hammer wasn't in the audience, I wouldn't tell you the story, but since he is, the idea of the idea space model came about from David Hammer, but always talking about shopping for ideas. And I kept thinking, what happens if you have a bag and the ideas start falling out? And so using that together with, I think I just read by Kotsky's zone of proximal development, it all seemed to come together into this scheme over here, which was the idea space model. And I'm not going to go into it in detail, but it's a geometrical metaphor that summarizes the result of backstage cognition processes, both the conceptual ones, of the kind that I've pointed out, and ones to do with affect. So, one can look at this as, from the following perspective, you can say what resources end up in working memory that can be used productively to engage with the task at hand. And what affect does is it closes that space and then reduces the resources that allow you to engage with the task. So, just sort of crudely, one can say that the quality of engagement is related to the size of the space. So, a big idea space, will allow for high quality engagement, and a small idea space for low quality engagement. There was a sort of PERC talk that I think I gave in 2010 together with Deidre. So one of the interesting things, this is of any use, one of the interesting things that was done with Jennifer Roth, who was at Oregon State University, did the following. She studied the effect of instructor moves on the quality of engagement in an introphysics class for engineers. So basically looked to see what, if someone said, think of this or do that, and then looked at whether the engagement that ensued was of a good quality or not. And then what was quite interesting was the following, that what she then did was to put down the practice that she observed and separated out those practices that led to high or low quality. And what was interesting was that they fell into two categories, both which would be explained by the idea space. I'm not going to go into it in detail, but for example, if you tell students this is an easy question, will that make them have low quality or high quality engagement? In the ideal space model, that's a bad thing to do, because if you say that, it introduces monitoring, and monitoring reduces the ideal space, the quality of engagement is going to get lower, and is that what you observe? And that's exactly what you did observe, and so it gives you some interesting ideas of how you can produce materials possibly, that use the idea space as a shorthand for taking in all these factors from Africa. More recently, it's quite interesting that my student Mumene has done, looked at lab engagement, and what we found there was that there was a very strong, well, there were obvious things about, students don't always like lab for all kinds of reasons. There are obvious reasons, but a set of reasons that had not actually been apparent to us were socio-emotional reasons. There were sort of things where students felt that if they were graded badly, they had learned something, but then they got graded badly, and it made them feel bad. And that wasn't pleasant, and they didn't like that for that reason. A whole series of things like that. And by taking the idea space and plugging it into a model, a lot of these observations have made sense to us, and we're kind of working on that. So that's that model. So, so to summarize, I think that physics as an enterprise comprises both empirical experimental data and evidence, right, and the theoretical, which I think we can now call ontological innovative constructs. And what those things do, they reduce the complexity, and in doing so, allow one to interpret the key features and also allow one to decide what to do next. So they interpret that prospective guidance. I haven't spoken explicitly about the DBR, but a lot of what I've read has been from that literature, and that's a very new theoretical approach which has to defend itself, in the social science literature. And what it's done is it's problematized, and I've taken this phrase and pushed it a bit further, the humble pragmatic theories, and they claim that these theories, in the service of knowledge production as well as for prospective and pragmatic design, form a core part of design-based research. I see DBR as something extremely useful for us to look into. It may not turn out to be productive in the long run, or it might, but at this point I find it really interesting. It seems to be one of the theoretical frameworks that allow one to take research findings and put them into complex situations, make running repairs, and is a way of actually encapsulating that experience. And then the last 2 points, I think that I don't know if you agree with me or not, but it's quite extraordinary the parallels between nuclear physics and PER. I read, in fact, I had to cut out 2 or 3 pages of the Nobel Prize speech, because very often, if you read the Nobel Prize speech and you take the word nucleons and you take it out and you put students there, it actually makes absolute sense. And there was one phrase, I wish I kept it, that spoke about, it was so cool. It said, in some cases, you find that one nucleon is simply a spectator, while in other cases, they're all active participants. But if you look at the Nobel Prize speech, it's quite extraordinary. So I think that nuclear physics sets an example for producing humble theories that are rooted in empirical data, and it provides insight and portabilizes, if there is such a word, the knowledge. And I think PER has this incredibly rich base of empirical studies for generating humble theories, and these are rooted in the tradition of physics itself. So I think in conclusion, I think humble theories help in understanding the data. They can provide guidance in how to proceed and make the knowledge more portable by reducing the inherent complexity, by freeing the data to some degree from the contextual aspects in which they were gathered in the first place. Thank you.
Thanks very much, Saalih. So I'm sure he's left plenty of time now for discussion and comments and questions. So please, Rachel.
you turned off your slides, but the slide had 3 big bubbles on it, the empirical data, the conceptual model, and the mental model.
Yep, I'll get that.
Like 4. Sure. I noticed there's no people on that slide.
Right?
So this is a theoretical structure in which a person is their mental world.
Well, the students are in the physical world.
Yeah.
And I just wanted to invite you to reflect on that. Do you have anything to say?
Yes, now I simplified the diagram. You see, it says here real students and engagement process. I didn't actually point that out. I think I snuck that in and forgot to mention that. So I think that when we deal with real students and we look at classroom situations, these are very complex, and I think in some ways one has to reduce the complexity. So when we observe, I mean, you know, whatever actions we produce in the classroom and perceive, I mean, those are actually reduced in any case. So I think, and although I put this sort of brain here in the mental model, I think it's obviously a lot more complex, but the observation itself, I think, you know, is already takes some of the complexity away. I mean, you can't observe everything, but if one is prepared to create some of these, you know, some of these ontological constructs, I think it allows one to see patterns more deeply. So I think even the talk on networks, you know, just by being able to simplify some of the complexity in the verbal, you can actually get other patterns. So no, I do not intend to reduce the students to, you know, just that, okay? I think that when one looks at students, there are certain things that you observe, you know, you can say something, you can behave in a certain way, and you can write something. I mean, those are the 3 observables I think that one looks at. And so I think that takes the student and, in a sense, you know, creates 3 kinds of complex variables out of that.
Valerie.
I very much appreciated the approach of humble theories and the value that it has for exactly that last point that you made in making our ideas portable and a little more generalizable from the particular context that they're in. But I wanted you to reflect on the question of, so are you saying that we're good with little humble theories that can help us move our ideas around? Or are we aiming towards something that's a little bit more of a theoretical superstructure to help us understand learning?
I think that's a great question. I think that if one looks at the way in which, you know, nuclear physics proceeded, then initially you're able to describe a certain set of phenomena using a certain description. And I think, you know, it could be a very humble theory or it could be a humble theory, but what it allows you to do, I think, is if there's value to be added to connecting to bigger theories, I think that's worth doing. It's not always clear that is worth doing, because sometimes, you know, so for example, if one were to decide to understand the certain phenomena of the nucleus, and you started out with some fundamental theory, it's so far away that it doesn't actually have any practical significance. So I think the question that you ask, I think, depends on what it is you're trying to do. And if you're trying to explain something that's very localized, so if you start with the data, I mean, the data are there and they apply to this group of people. You then try to reduce the contextual dependence, and that might be a very humble theory. You may then decide, oh, I'm trying to do something more sophisticated, but for that purpose you need to connect up to some of the bigger theories. So I think I see humble theories, you know, and I think in a sense it's this, you know, it connects, a series of humble theories can eventually end up as a grand theory. But then if one looks at how we do physics, very often in practice, you know, you start out and you say, oh, to solve Maxwell's equations, but at the end of the day, that's when you start out, but at the end of the day you make a whole pile of approximations, you do a whole host of things to actually fit the situation at hand. So I think it's the connection between that. I think that what I was trying to say from at the beginning was, if we try to connect our local data to our grand theory immediately, I think it's overpowering. If you stick only with the data, I don't think you actually make it portable enough to be able to communicate it to other people. And so I think I see humble theories as mediating between the two.
Me?
Yeah.
Well, Sally, thank you so much. I am really excited to hear you talking about design-based research, particularly for this community, given that so much of what we do is designing learning environments. And I guess I wanted to hear you think a little bit about, right, so one of the sort of fundamental tenets of design-based research is the notion of having design principles for learning environments that we create, and those design principles that are based on empirical evidence from other studies. And I guess I want to hear you speculate a little bit on, based on your reading of PER, could you think about what might be some of those design principles that our community might start to rally around?
I think I maybe want to say something one step back.
Sure.
I think that, when one looks at the way, so I think we have lots of very interesting fundamental findings. And one of the things that always, tends to be a criticism is, but why are they not used in practice? I mean, that's always like, no, there is a huge divide between the PER people and the practitioners. And but the point is that, and I'll say this is probably extreme, nobody who studies nuclear physics is immediately asked about how they're going to design a power station. I mean, there's a link, okay, but it's not a simple one. And I think the link between that is, in a sense, prototypes and engineering and an engineering approach. A classroom situation, a curriculum, is essentially an engineering problem. And I think that's what we don't have. We don't have a model, and I think DBR does seem to offer a way in which one can take a basic research finding and see how it works in the complex context, and then document that, because it's not going to work exactly the same way. So I'll give you an example of something that I saw someone do recently. They used an inquiry-based approach to pre-service teacher training. And what they found was, when they had applied the method, no one seemed to really understand the principles of what they had been taught. So he had to make some running repairs and do a sort of bit of a summary. Then the next year round, he did the same thing, but he made a better summary. And at the end of the day, he decided he would do all the inquiry based and then give a traditional lecture. Then everything worked very well, but he was depressed. He said, because why did he have to give the traditional lecture? But giving the traditional lecture at the end of an inquiry-based, course is not the same as giving it at the beginning. And so he kept this, in these cycles, he was able to come up with a practical way of using inquiry in his context. And I think that is important. And what design-based research does, it seems to me, is to provide a vehicle and a means of formalizing the kind of thing that we often do. And if we do it that way, I think we can communicate it to each other as well.
Thank you.
Sorry, with the questions.
So my question depends in part on my interpretation of what you're saying, so I'll say what I heard you saying. So one of the things that I'm hearing is, in talking about theory, is kind of how we can generate theory from our interpretation of data and then maybe use that to cycle through. And one of the things I'm wondering about is where, a different way that I think about using theory is drawing on existing theories to understand cases, but also using what's going on in that case to extend or challenge or refine the theory. And I'm wondering if you could say how that fits into what this conceptualization.
I think that I would immediately say that's a very complementary approach. I think that, for many people that would be the way to go. And, and if you're happy to go that way, I think that's great. But the problem is that when you're rooted in the empirical and you don't quite see that link, I think that in our own physics tradition, we can see that there's a way forward. And I think that's really what it is. I think the role of humble theories complements that. I mean, if you're able to use a theoretical lens that's very useful, or you borrow pieces from that. I mean, I think that's the complementary approach. So I mean, I certainly don't see it as this is the way. I think this is something to add to that, to help the theorizing that we do a much broader sort of enterprise.
So I noticed on the previous diagram, slide before this, there's no bubble for social or political elements in the modeling. And that, I would argue, is important both for the nucleons and for the students. The nucleons, it presents us with a choice of whether we want to create almost limitless energy for everybody, or whether we want to create bombs that can kill a lot of people. And the Hubble theories are not immune from that choice. The droplet model is instrumental in making the bomb. So I'm thinking of what's the analogy, at the risk of pushing the analogy too far. What is the broader purpose of doing this research, and how can it guide whether we decide to do whatever the equivalent of free energy would be, or the equivalent of for students, like what do we want out of doing this research?
I think the question really, I think that is the question one would ask whoever embarks on doing what they're doing. What is the purpose of it? But I think okay, let me just summarize what I think I'm trying to say. What I'm trying to say is that in the enterprise of physics, which is this, okay, I mean, and there are no, this is, in a sense, if one thinks of how this particular diagram was used to explain the Newtonian world, right? And I mean, there aren't many socio-cultural aspects in Newton's world up here. I think we all agree on that. I mean, the point mass and the physics bus and all that stuff, I mean, they're all existing there. So the analogy is that people do that for the physical world. We have an enterprise which is part of physics, and so I think that when we decide to embark on a study, and it could have a broad socio-cultural perspective, I think that we are within the traditions of physics when we generate some theoretical model based on that data, whatever the purpose of that is. And that may be, an extremely, socio-cultural purpose. So I think it's really, the question really is that one should not limit oneself to thinking, okay, so I'm going to go one step. I've been maybe not wanting to say this, but I'll say this now. It's bothered me for a long time that, especially in the university that I'm at, that when people talk about education, they tend to immediately want to use theories from social science. In fact, we hardly ever, they use sociocultural theories, but they often, we don't often even go towards educational psychology or so. So it's interesting to ask why that happened. And in fact, the group I was talking about, we've tried to discuss that. And so I think, what I've tried to think was that in order to say to ourselves, we come from this tradition of physics. Physics education research fits into that. Here is another way to go. There are other ways to go. I mean, the one that we, spoke about, you can borrow the theory, and you may want to use a sociocultural theory or educational psychology. I mean, these are all ways to go. But I think that often, if one comes from a physics tradition in a physics department, those things seem very alien. But I think the purpose of what you set out to do will determine how you theorize and whether you humanize or dehumanize what you're actually doing.
There you are.
It seems to me that the products of ontological innovation, which form the constructs that Hubble theories are constructed from, are generally entirely unknown to the agents with which they're associated. That is to say that the things that Hubble theorists invent as structures that are in the mind are beneath the level of conscious awareness of learners themselves, often. And that strikes me as very mysterious and kind of wonderful and very inconvenient for us. I'm wondering if you could comment on that without using the word metacognition.
Is the time not up, Sylvia? Andrew, I think
It's
that,
5:33.
Andrew, I think that's a very deep question, okay? And I think that I don't think one can foresee what those constructs will be. Unless one actually tries and embarks upon that. I don't even think they may not even be unique. What's exciting is that they can become a stepping stone to some very large, powerful theories which give one larger insight. And I mean, and those theories are often very abstract and extremely mysterious. So I think if it's mystery that you want, I mean, you can maintain that all the way up.
Okay, well, I think that's a very good place.